This is physics course division 4.1 till 4.2. I apologize for the bad mic because I'm not in the country. But anyway, it shouldn't be too long. It's just 2 pages, 3 pages, yani 2.5. It should be yani half an hour, easy. Yeah, let's start. Okay, so the first thing is design an experiment to demonstrate that if wire is moving, a current will be induced. Remember, all of chapter 4 is about, why is this so big? Is about the idea that F be I. So when you have a force in a magnetic field, it will induce a current. So انت عندك مثلا magnet مثل هون, and you have a wire and you start rotating it, spinning it around. Okay, that's a force inside the magnet field, so there will be an induced current. That's the whole idea of this chapter. So here they're saying design an experiment to show that a current will be induced. It's very easy actually. Just get a wire and start moving it, and if there is going to be induced current, an ammeter will register current. Very easy. It's over here. Ammeter will register current. Okay, so you can read this if you want, but this is more of understanding. These questions don't really come. This is just so you understand what's going on. Question 2, describe an experiment to check the rule that the induced current takes a direction to oppose the change of flux. Again, these are things that they don't ask you to design an experiment, but just to check your understanding. So over here, again, same pendulum as the top one. Let me turn on the editing. The same pendulum as the top one. We observe that moving the wire by hand towards the left produces an EMF such that the positive charges flow from A to B. Using the right hand rule, the motive force, okay, explains why the pendulum is okay. Basically, you just have to know, you don't need to know the experiment, but basically you need to know that Lenz's law, the induced EMF opposes the شو اسمه هاي الدايركشن نسيتها. Okay, well, there's a question for Lenz's law, but I forgot it. But you should know that the induced current, the direction of it is opposite to the change that's creating it. That's Lenz's law. Yeah, that's Lenz's law. The induced EMF is, the direction of it is opposite to the change that creates. And you guys know the induced current results from a change in magnetic flux. So this is actually Lenz's law. The induced current takes a direction to oppose the change of flux. That's Lenz's law. But that's later. Anyway, what are the conditions necessary for a charge to experience a magnetic force? This also you need to memorize it. There's nothing for me to explain here. Now when we say to experience a magnetic force, in other words, we're saying induced EMF. Okay, electromagnetic force. Okay. How do you get an induced EMF? Remember, F, B, I. Okay, so there needs to be a force. So if you get this coil and you don't move it, there won't be any induced EMF. There won't be an induced current. So for that reason, it needs to be at motion. It can't be at rest. Okay, so if you look at the answer, it's very easy. The charge just has to be moving, obviously in a magnetic field. If it's not in a magnetic field, there won't be any EMF. Anyway, a positively charged particle is moving to the right under an influence of a magnetic field moving down. So this is the motion is to the right, so the force is to the right. The magnetic field is down. And okay, they're gonna ask determine the direction of they want the magnetic force. Sorry. How is this the force? This is the current. This is the current because it's a charge moving to the right. Obviously, when charges move, that's called electric current. So they gave us I, they gave us B, and they want us to know where is the direction of the magnetic force. To do this, you're going to need to use the IBF, FBI rule, whatever you deem fit. And now I'm going to use the IBF rule. If you take your thumb pointing to the right, imagine this is I. Okay, then you take your index finger as the magnetic field pointing downwards, right? Then you extend your middle finger. It's gonna be going inwards. Like how can you look at it from here? It's gonna. I don't know how to draw this. Man, I wish I could turn on my camera, but I'm on my tablet. I can't set it up. I think it's like this. Okay, so this is I here. This is B going down. So F would be pointing inwards. Okay, so I hope it can kind of like, you know what I mean? These are like perpendicular. Okay, so I think at this stage in physics, everybody should know how to use this 3-finger rule. IBF. So the answer should be into the page. Let's check. Based on the right hand rule, it should be into the page. Yes. Okay. Question 5. A rectangular wire ABCD is connected to a galvanometer that measures in the induced EMF. The wire is rotated at a constant rate inside the horseshoe magnet. Constant rate. Okay. Then they said, how can we increase induced EMF? If they said constant rate, some people might not read the question. They just say increase induced EMF, rotate faster. Many people say this. Wrong. يعني قالوا لك constant rate. You can't say rotate faster. What are the two things? Remember we said rotate faster, right? Rotate faster, and we said increase the number of loops in the coil, right? And obviously, since we can't use this because they said constant rate, we're going to use this one, increasing the number of loops in the coil. But let's check. Using a stronger, yeah, oh, okay. This is wrong. But this is good. Why is this good? Because I don't have access to my notes right now. Well, I do if I open the drive, but I'm in a different country and I'm not in the mood to open my drive. Actually, not, I'll open my drive. Wait. So before I open the drive, these must be memorized. They come every exam. And by the way, these grids, you need to know them. It's not a choice, like you have to memorize these, okay? Know them, because they always come. And I'll show you the sample question sheet that I have. Just give me a sec. But these, you need to memorize them, okay? Using a stronger magnet, obviously. Rotating the wire faster. I forgot about stronger magnet. Rotating the wire faster. Remember, F, B, I. You want to increase this, you need to increase this and this. If you increase the force, you rotate it faster. If you increase B, you're using a stronger magnet. Increasing the number of turns obviously is correct, and using a wire with a bigger surface area. These are all correct, but they don't really ask the surface area one. I haven't seen it yet, but to memorize it. Let me open up some documents that might help, and obviously all of these will be sent on the files group, the grade 11 files. So this full document must be memorized if I were you. I'm sure half of these questions will come at least, except this one. This isn't coming. Question 11 isn't required for the material, I'm pretty sure. Let me check if the oscilloscope is required. 1 second. Okay, so I checked it, and the oscilloscope is required. It's 4.2.6, as well as the dynamo, but I haven't seen any questions come from the dynamo. This isn't required because this is for transformer. Question 13 is not required. So up until question 12. Anyway, let's continue. Why I'm sketched out is because I haven't seen any questions about the oscilloscope or the dynamo in the course revision. So I saw it in the sample questions, so you should know it. Okay. State Faraday's law. Faraday's law, I think it says that upon having a change in flux, there should be an induced EMF. Let's check. Faraday's law says that the induced EMF is directly proportional to the change of the flux. Yes. So again, these are things you must memorize. Faraday's law, whatever, Lenz's law. So you should know induced EMF is directly proportional to the rate of change of the magnetic flux. That's why we say, مثلا, if you want to double the induced EMF, double the number of loops in the coil, because when you double the number of loops in the coil, there's going to be double the magnetic flux. Okay, which I think this is also, let me see, like this is مثلا, they didn't, it's not here, but obviously guys, don't rely solely on the sample question sheets. I'm only going to be able to send week 2 and week 1 because I think also that's what we need, but I don't have the file, my computer isn't with me, it's back in the UAE, so I won't be able to send all the files I have. Let me continue. Obviously, if watching for finals, I should be able to send. Part B, list 3 actions to increase the induced EMF. To increase the induced EMF, you can use a stronger magnet, rotate the wire faster, double the turns of the loop. We know them. The actions: the faster the magnet's moved, more powerful magnet, more turns. Okay, Lenz's law. I think they asked it. What is Lenz's law? Of course, stated. Lenz's law states that the direction of the induced EMF is opposing the change of the flux, right? Then here they said indicate the direction of the induced current shown below. Explain your answer. So the coil is being pushed in, and obviously this is the X, means the magnetic flux is going inwards, right? When you have induced EMF, induced current, remember that it opposes the force, right? So actually, when it's being pushed in, the force that we're going to get is going to be what? To the right. Okay, why is this important? Because when you use your right hand rule, what's going to happen? If you use the force being to the left, you're going to get it wrong. You need to use it opposite to what they give you. The coil being going inwards, well, now you need to use the right hand rule. Using your thumb using your thumb as the force and the direction of the magnetic field coiling coil, like use your thumb. I did this in a previous CA video. If you go to term 2 week 3 or term 2 week 2 CA, I think term 2 week 2 or term 2 week 3, one of them, but go watch one of my previous physics CA's videos and it will be there. Trust me, it will be there. I do remember putting camera and showing how to do it. But you use your thumb as the force, so in this case to the right, and you use the rest of your four fingers. You stick your thumb out and you close your fingers. You use the rest of your four fingers at the direction of the magnetic field. The magnetic field is going inwards, so you just coil it inwards. So I'm going to the right, going inwards. Like, how can I explain this? It should be going down. Let's see the answer. I did it in my hand, it went down. Let me see what they got. No, I should oppose, so it should be outward by the right-hand rule. Anti-clockwise. So anti-clockwise. Let me see. Going inward. Yeah, okay. So I did it. I'm gonna try and let you imagine it, okay? So this is your thumb, okay? This is your thumb over here, and this is the rest of your four fingers, right? So until you take your thumb, since the force we said is going to, let me go to the other page. Okay, I did the same question in the previous CA video. So you have your thumb over here, and you have your four fingers over here. Okay, so since the force we're taking is to the right, and the force is to the right, and the magnetic field is inwards, you take your fingers and you kind of like put them inwards. You know what I mean? So this isn't up. They're not facing up. No, they're just facing like inwards, if you get what I mean. Now, if you curl these towards you, or just curl them, it's going to be curling like this, right? And this is the anti-clockwise direction, okay? Lenz's law is always anti-clockwise or clockwise. In the exam, how did it come? It came copy-paste like this. It's being pushed outwards, and the magnetic field is inwards. So if you use our famous law, since going to the right, we oppose it, we go to the left, it's going inwards, and you use Lenz's law. So you have the thumb is like this, and these are the fingers, and you coil them, and they should be clockwise, okay? Because when you coil these, your thumb is to the left. When you coil this, it's going to go down, and it looks like this, looks clockwise, okay? This is how it came in the CA, by the way. Copy paste as this question 7. Okay, moving on. Alternating current. Sketch a graph of the current value against time for 2 complete cycles of an alternating current of peak value 2 ampere and frequency of 0.5 hertz. Indicate with a horizontal line on the graph the approximate value of the RMS current. This question is very nice, actually. Maybe they don't ask you it in, I don't know, I haven't taken a look at the past papers required. Maybe in the written they ask you, but it's definitely required if you're doing the IGCSE. And this actually sums up your understanding for the concept. Maybe 4 pages in the book, 3 pages in the book are required just to explain this one question. Why is this nice? Why I can see it coming in the written. I still haven't seen the past papers, and please don't rely solely on the past papers, because they said in the material, and it was written that external questions, like unseen questions, will be given in the written. Okay, this tests you on the VRMS, or in this case IRMS. It tests you on the graphing, and it tests you on the formula T is equal to 1 over F. Okay, let's explain one by one. When you graph a current time graph for an alternating current, you know that the DC current هيك شكله, صح? Because it's direct current. But alternating current, we know it's sinusoidal, right? Sinusoidal as in it looks like a sine function. طيب I'm gonna draw this for you over here. Okay, not straight but yeah, straight. Okay, وهيدي هون كمان here. Okay, and I'm gonna help you understand. The first thing we can see, and I think everybody should be able to understand this, the peak value is 2 amperes. Everybody studied geometry last year, and you know that the sine graph has a maximum peak and negative peak. These are both the same value of current, they're just different directions. There's no negative value of current. This is also just 2 amperes, but just in the other direction. Let's say this is going to the right. This is just also 2 amperes, but just going to the left. Okay, this is why we go down, because it switches direction. Okay, it's a good idea to label your graphs I measured in ampere, because we said we're looking at current against time. Current is in ampere, time is obviously in seconds. So you label this, and you know it looks like this. Sine graph. Type sine graph. I think I made it look a bit tricky. Sine graph looks like this, right? And we just repeat again and again and again. طب you're gonna say, طب okay, Walid, you drew for us this. How do I know? أنا what how much is it here? How much is, like, what's the time? It's perfect. They told us the frequency is 0.5 hertz. You need to know that frequency is actually 1 over period. Or other people, I prefer using this formula, T is equal to 1 over F. Okay? T means time. But why do I use capital T instead of small t? They're both time. But capital T represents the time of one period. Okay? Or the time taken for one rotation. Okay? This is a very, very, very important formula if you're doing IG physics. We're just moving on in general in physics. You need to know this. So obviously in this case T will be equal to 1 over 0.5, which is equal to 2. So here's what you do. You draw your sine graph. Again, don't make it like, people are gonna be perfectionists and they like make it too perfect, whatever. Nobody cares. As long as it's curved and it kind of looks okay, that's what the examiner or the corrector looks for. This is correct. Okay, labeling here 2, here 1 is perfect. Obviously, if this is 2, then halfway through it's going to be 1, right? So this would be correct. But if you want, you can, and this is what I would prefer, is just what they did in the answer key, is they continued on and did another cycle. Wait, no, it's ignore it's a bit bad. But I'm not sitting on a desk. I'm just sitting on a chair with a tablet in my hand. Okay, خلاص. So if this is 2, another 2 seconds would make this 4, and would make this 3. So this is how it would look. Again, on paper it's way easier to draw, but try and make them the same length. Like this did not reach 2. I should fix this. I'm not gonna give you wrong answers. Okay. Okay, hold on. Let me cut 2 when I get it right. Okay, so I kind of fixed it, but this way they both reach -2, and they both reach 2. And they left out, I forgot one part, is with a horizontal line, graph the approximate value of the RMS current. To find IRMS, you just take I max over radical 2, right? So you just take 2 over radical 2, and just give me a sec. It's gonna be 1.4. Let's just say 1.4. Okay, so you go up here to 1.4. If this is 1 over here, you go to 1.4, which is about here. And using a horizontal line, I'll use black. So over here, with the ruler, of course, please make sure you use a ruler. Heck, you can label this IRMS. Perfect. Let's take a look at the answer key over here. The current is periodic. They found the time, which is 2 seconds, and they solved. Very, very easy. Okay, and like I showed you, they did one period and did another period. Okay, question 9. Let's go to the question. Okay, describe how an alternating, let me erase this all, it's ugly. Describe how an alternating current is produced in a loop. So they want the principle. Let's go to question. Let's go to answer key just these are the explanation questions. I'll just give you the answer key. You have, how do you get an alternating current? You have the magnet, of course. Remember, this is too big, no? Remember, to get an alternating current, F, B, I. You need F and you need B. Oh, that's disgusting. حاولها برا. هيك. هيك. Okay, anyway. You need a force and you need a magnetic field. That's why you have the coil for the force that you're going to be turning, and you need the magnet for the magnetic field. So when the loop ABCD is rotated, the flux entering the loop will vary with time. Remember, to get I, always think how change in flux, right? Deflux. So when you rotate the loop, there will be a change in flux. And what's gonna happen when you have a change in flux? Obviously, you're gonna have an induced current. And since you're rotating it, the current will change its direction, right? انت بتكون هون, okay, every half a rotation is gonna change its direction. This is actually, you need to know, by the way. It's gonna change its direction depending on the orientation of the loop with respect to the magnetic field. Again, we're gonna cover this later, and they should do it here somewhere. Oh, that's a lot, yeah. Okay, they didn't say it here, but remember that it changes every half rotation. The AC. Oh wait, they said it here, no? AC generator. In that case, the two brushes. Yeah, okay. We will get to it later. Type. But you should know that very, very easy. If it comes in the written, okay? If a loop is rotating inside the magnetic field, it causes a change in flux. It will cause a change in flux, which causes induced current. What's gonna happen to induced current? It changes direction. You could say later every half loop. This question, I don't know why they brought it now, because they asked it twice. They asked it now where they explained it briefly, and then later, what am I doing? And then later where they explained it in detail. I'll prefer to explain it in detail rather than explain it briefly. Okay, a current time graph is shown below. What is the maximum value of the current? Obviously 5 ampere, right? Indicate two instances at which the current has zero maximum value. Indicate two instances at which the current has a maximum value. You could say here 25 ms and 125 ms, right? Okay. Indicate two instances at which the current is 0, 50, and 100. What's this question? This is what we like to see. The current changes its sense. Name it the first time it changes its sense. 50 ms. When we say changes its sense, goes from positive to negative. Okay, so هون كانت positive, هون راحت negative. When did it cross the 0? At 50. What is the frequency of the current? Remember, T is equal to 1 over frequency. If you switch up the formula, remember, the denominator you can substitute with what's there, or cross multiply. You're going to get that F is equal to 1 over T. What is our period? How long did it take for one complete cycle? 100 milliseconds. Please do not do 1 divided by 100. It's millisecond. So you divide the time by 1000. 100 divided by 1000. So 100 divided by 1000, because it needs to be in second, is 0.1. So you're going to get 1 over 0.1, which is 10 hertz. Okay, the unit of frequency is hertz. Let's check our answers. Okay, the maximum is 5 ampere, 25, 125, 50, 150, period. They asked period? Oh, they didn't ask period. Then, okay, 10 hertz. Very easy. IRMS. Okay, this is very easy. Calculate the IRMS. Of course, to calculate the IRMS, very easy. It's just equal to I max, peak current, divided by radical 2, right? And they did it here. They got the answer. 2.1 ampere. Don't forget the unit, though. Two different methods. What is the difference between alternating and a direct current? Develop your answer using sketches for AC and DC. Whenever you look at alternating and direct, what is the main difference? Obviously, alternating current changes its direction. Alternating current has an alternating value, but direct current does not have an alternating value. It's a constant value, right? And when you look at the sketch, how do you know which one's alternating, which one's direct? By looking over here at the brushes, right? By looking at the brushes as well as over here. So for A, like مثلا, I think they got it in the CA. They asked you what is A, what is B, and here's how you look. The one with two slip rings, two slip rings. They give you this picture. This is obviously AC, and the one with one split ring commutator, that is DC. Okay, illustration A is alternating. It uses a slip ring, and the current changes direction continuously. B uses a commutator, split ring commutator. That's how you know it's DC, direct current. Okay, it keeps on one direction in the rotating coil at all times. Remember, which one has only one direction? DC. It's called direct current. The whole point of the split ring commutator is so that the wires are always in the same direction. The current is always moving in the same direction. Okay, very easy questions. And CAE questions, they all come from these grids. And I'm seeing these grids, I'm reading them. I've seen this before. Okay, then AC, DC. Describe, and they obviously gave a good explanation in detail. أول شيء, the DC, right? A loop of wires able to rotate is placed in between the arms of a horseshoe. As it rotates, the magnetic flux changes continuously. Remember, نحن, our generators all come from the rule, from the there's a word I'm forgetting. Anyway, from the rule FBI, that the change of flux gives me the current. Okay, we're trying to produce what? Generate what? We're generating current. Okay. As it rotates, the magnetic flux through it changes continuously, thus inducing a continuous current. So change the magnetic flux, معناتها عندنا induced current. When the loop, okay, this is very important, right? When the AC, this is the first one we're doing is AC. When the loop becomes parallel to the field, the flux becomes zero. And just because they asked this before and it was in the quizzes, when it's parallel, I max. When face is parallel to B, and then I min when face, or no, it's zero, huh? I think, I'm not sure if it was zero, when face is perpendicular to B. We'll explain this again in a second, but let me finish reading. Beyond this point, the flux through the phase starts increasing. The induced current starts to oppose the change in flux. As long as the change in flux is taking place in one sense, the direction of current does not change. However, as the loop shoots beyond the position which is normal to the field, the flux starts decreasing and the current starts changing direction. The current is taken out of the coil through a twin ring or slip ring commutator. Okay, so let's summarize quickly. أول شيء, we're going to say that the loop, there's a change in you rotate it, that causes a change in magnetic flux, which causes an induced current. This is the first thing. Rotation causes a change in magnetic flux that causes an induced current. You need to know that it's going to keep on rotating. When the face is parallel, you have reached the maximum current. Why? Remember, when the face is parallel, there is no flux. You're going to say, Top, there's no flux. How's their current? Remember, it doesn't depend on the value of the flux. It depends on the change in magnetic flux. The change in magnetic flux is maximum when the flux has reached zero, because going from 5 to 0 is it's a bigger change than going from 5 to 3. You know what I mean? So this is why it's maximum when it's parallel to the magnetic field, and it's minimum when it's perpendicular to the magnetic field. Type. So these are the two very important notes that came in the CA, and I think I remember seeing the question. They asked which one is the face parallel, one is it perpendicular, and they gave us pictures of the. Anyway, you need to remember, here, okay, they're talking that when does it change? It changes over here. Let's say you have, this is the north, this is the south, right? When the coil is perpendicular to the magnetic field, okay, this is when it changes direction. Remember, it changes direction every half. طب okay, every half rotation. طيب فهمنا, but every time it comes perpendicular over here, and goes in. Every time it's like this, it passes through perpendicularly. It's hard to draw, but every time it's perpendicular to the face, to the magnetic field, that's when it changes direction. Type. So rotation causes change in magnetic flux, causes induced current. Induced current maximum when the face is parallel to the magnetic field, minimum when the face is perpendicular to the magnetic field. And then remember, it changes direction every half rotation when the face is perpendicular. طيب. Oh, by the way, actually no, not even I meant zero here. Oh, it's 0 when the face is perpendicular to B. Why 0? Because when you're perpendicular, you're starting to change direction. Remember, we have the sine graph like this. When you change direction, over here you're starting to change direction. You change direction at 0, right? And this is actually when you're perpendicular. Okay, so it's minimum when the face is perpendicular to B. And in other words, 0. Don't say minimum. Minimum, because some people might see minimum as the lower point. Some people call this the minimum. This over here is just the negative maximum. I don't like saying minimum. Okay, I call it negative maximum. طيب. هلا DC. They said DC generator. And AC can be transformed to DC. How? If you get the slip rings. I remember here for AC we said we use slip rings. Okay, twin ring or slip ring. For DC, you change the slip rings وبتحط لها commutator, like the DC commutator. Okay, the split ring commutator. In that case, the two brushes are arranged so that as the coil goes through the vertical, an exchange of contact occurs from one half. This way, the EMF reverses every half a cycle. Okay, hence one brush remains positive and the other negative, which is equivalent to say that induced current flows without changing stance. AC is thus converted to DC. Not much to know here other than the fact that DC utilizes the split ring commutator. Okay, question 15. Hey, could come the last question. I don't know why I opened it. Over here, 15. An alternating current generator is rotating in an area of an external magnetic field. The induced EMF in the loop in the generator as a function of the angle between the surface of the loop and the external magnetic field is plotted in the graph below. Determine the positions at which the surface is perpendicular and which it's parallel. Many people saw the answer and they got very confused, and I'll show you why. They said it's maximal when it's perpendicular and it's 0 when it's parallel. Okay, people said, oh, the course division is wrong. Let's see. Some people said it's wrong, and then other physics teachers came and said maybe the question was just not clear. Here they're talking about this is the angle between the surface and the magnetic field. So over here, when this is the north, this is the south. Okay, when the magnetic field is like this, let's say parallel, when it's parallel, okay, and this is going like this, going straight, right? When it's parallel, it actually is making a 90-degree angle with the normal to the surface. So this is why this question is actually correct. It's not wrong, but they just worded it in a way that you can't really understand. Here, it's representing the function of the angle of the normal. That's what they're trying to say. Okay, when you say the surface of the loop, أظن normal تبعت الsurface. Okay, if you look at the normal, it's actually making a 90-degree angle when it's parallel to the loop. So that's why this is correct. But the way they ask it in the exam, they never say normal. They never say. They say it's parallel, parallel over here at B and at D, and it's perpendicular at C and at A. So that's why here in the solution, because they're talking about normal in the question, in the solution they said it's perpendicular at the maximum point. So here they said it's perpendicular at B and at D, and parallel at C and at A. This is correct because they're talking about the angle between the surface and the magnetic field. If in the exam they got you angle between the surface and the external magnetic field, this would be correct. Just switch them up. But 99% of the time they never do this. In the exam they just tell you it's just the angle of يعني the coil, between the coil, not the surface. So that's why in the exam نحن we're used to remembering, as I wrote up here. شكلي I erased it. No, it's in the solution صح. As I wrote in the solutions, it's maximum when it's parallel, it's zero when it's perpendicular. This is what you need to know. If they said surface of the loop, surface of loop, it's the opposite. Okay, just switch them. But they never ask it. ماشي. هيك بنكون خلصنا 4.2. But before I finish, I want you to know this as well as the dynamo, which is in my notes. I'll go to the notes and I'll explain it. This is what we call, I'll just open the notes, wait. I just remembered I don't have notes on the dynamo and oscilloscope. I do have them written, but they're in my copybook at home. I'm not at home. So just read the book for dynamo if you want. It's a quick 1 page. It's just very, very simple. I didn't see any sample questions on it, so you do what you want to do. Personally, I would read it. This is the oscilloscope. You just need to know that oscilloscope is used for detecting electrons and whatever, and detecting detecting induced EMFs and whatever. Why we call it oscilloscope? Because it oscillates. Oscillate means going like this, like this. It's for AC currents actually. So you need to memorize just how to label it. Is the deflection plates, obviously they look like plates. It has 3 anodes, 1, 2, 3, and it has obviously the cathode over here. This is obviously called, the back part is called the electron gun. This is called the heater because it has a resistor. That's how I memorized it. If there's a resistor, obviously it's a heater, right? Because resistors cause it heating up. And the whole back part is called the electron gun. Basically, by the way, how it goes is it shoots electrons, they deflect over here on the mirrors, and they start shedding some light for you on a paper over here so that you can see basically what's happening. Very, very easy. The rest, question 13, remember you don't need this, is for 4.3, the transformers, which isn't required for our periodic. هيك نكون خلصنا. I just want to show you, by the way, expect unseen questions in the exam, just so you know that I'm not bullshitting. Okay, make sure if you want, go over the book. Maybe something wasn't mentioned in the notes, as in the course division. Usually I would have them in my notes, which will be ready for finals, but for this periodic, the dynamo, I don't have the notes on it, and oscilloscope, I don't have the notes on it, so try reading the book. I can't open ebooks on my tablet because it doesn't let me screen record. So thank you so much for watching, and good luck in your exam.